transmits lateral loads to the vertical resisting elements of a structure, such as shear walls and frames. And we kind of looked at shear walls and frames last time. So, but anyway, it's like really simple concept, right? So the building somewhere somehow gets this lateral force, but this lateral force has to at the end of the day, the only way the building can resist load is it's connected to the ground through the footing and stuff like that. So as long as, the force needs to transmit down to the ground, because otherwise you can't really resist any force, right? So there's got to be a system that transmits vertical load is easy, right? Columns and so, even if it's on the floor, it gets transmitted through the beam and comes down the wall or the column, and it eventually goes down to the footing. So that's super kind of like intuitive and makes sense. But lateral force also somehow, it starts this way and it probably gets transmitted through a floor slab or beam somehow, goes this way, but at the end of the day it kind of has to come down to the ground. So then what's called so we have this system called diaphragm, which is this horizontal element, oftentimes it's a floor slab, that transmits the lateral force and to a vertical resisting elements, right? So that's that's literally what the definition is. And I guess pretty much the only building I can talk about with full detail is the Broad Museum, which you've probably seen me talk about this 100 times. But in this case, this is fairly peculiar actually, but we have a shear wall on this side and actually that side too, right? So that's the shear wall. What it does is it takes the lateral load from diaphragm and transmits down to the ground. So that's what the shear wall does. What the diaphragm does is somehow, somewhere the lateral force comes through, it carries the lateral load and it transmits it to the shear wall. So in this case, the diaphragm is actually, so the one particular example here is so all of these gray thing that you're looking at is concrete. So this floor, which is the concrete slab, and the third floor, also this floor, these two floors actually works as one diaphragm. And the reason why there's so much concrete wall and columns connecting those two is that they can work as one diaphragm, which is, I guess it's kind of a peculiar example, so don't worry too much about it. But the idea is that there's this horizontal thing works as one thing and transmits the force to the shear wall. So I guess the only kind of fun thing today is this animation, which I kind of got it from the structural engineer, but this kind of demonstrates how that happens in a really, really exaggerated manner. But you can see how the building is trying to rock back and forth horizontally, but all the forces are actually concentrated to the footing, which is what you want to happen. How that's happening is through the use of the diaphragm and the shear wall, right? So anyway, so that's kind of the intro. And so there are roughly speaking, two kinds of different diaphragms. And so this is not a super nice slide or anything like that, but this is for a really quick explanation purpose. So there's a rigid diagram, and there's also a rigid diaphragm and flexible diaphragm. And we will be mostly looking at flexible diaphragm. But first, let me kind of explain what the differences are between these two, which is fairly simple. So basically, so let's say this table is a diaphragm, right? And these two legs or four legs are trying to anchor it to the floor. And you can do that. Unfortunately, it moves. But if these two are anchored, then you can see how if I rock this table back and forth, that back and forth force gets transmitted to this wall and eventually goes down to the ground. How this diaphragm, or in this case, the tabletop, that part is the diaphragm. How that behaves, there are two different ways, and it's kind of like there's no like strict way of, there's no like strict distinction between the two. It's all relative, but in one way you can assume this thing is rigid and it does not deform. So think of a concrete slab or something. Like it's relatively rigid, and and it's all relativity, right? Even if it's a concrete slab, if it's thin slab with not too much reinforcement, it's probably still kind of flexible in this direction. But in most cases, yeah. So if you assume this horizontal slab or plate is this one rigid thing that does not take any deformation, and that way, if I put a certain amount of force this way, right, like that, this whole thing, because it's rigid, it's gonna try to move as this whole thing as one, right? So hence, so that the dashed line is kind of expressing how this force. So let's say, so this 120K, what's shown here as this wide arrow, that's right here, that's the external lateral load that's being pressed onto the building. And then this diaphragm, because it's rigid, it's trying to move as a whole thing and up, right? And so the way the lateral load gets distributed among these different shear walls, so these are the walls. I mean, so this is plan view, obviously, right? Kind of a roof plan view. So let's say this wall, the length of this wall is 1. Length of this wall is half. Length of this wall is half. Length of this wall is 1. And it pretty much, because the whole thing tries to move uniformly, the amount of lateral force that gets distributed to each wall depends on the linear length of that wall, right? So in this case, this is linear length 1, this is linear length half, linear length half, linear length 1. So the longer the wall, it can take more force. So therefore, R is reaction. So this would take one reaction, this would take half reaction, one reaction. Therefore, I mean, this is just showing how it could get distributed, but it's like 40, 20, 20, 40. So if you add them up all, it's going to be 120. But it has to be resisting the other way, right? Because it's trying to push this way, so the resistance is that. So that part makes sense, yeah. And also, there's this assumption here is that apparently California building code, even though I'm not too familiar with the structural code, but apparently according to California building code, shear wall, so you build a shear wall and you can use that for your calculation as a lateral force resisting system. But it only matters, for example, if you build a wall this way, actually, because I have the 3D model here. So if you build a wall this way, right? Let's say that's the wall. It only counts in this direction, that direction. So, but you have to assume it's completely useless to that direction. In reality, strictly speaking, because there's a little bit of thickness there, I mean, it's got to be able to resist a little bit of lateral load. But to simplify, they would assume, I mean, just imagining it casually too, like it would be easy to knock down this wall this way, right? But it would be kind of hard to do that that way, right? So the assumption is that this wall, if the wall looks like this, it only counts in the long direction. So you can only count this as a shear wall in this direction, but you have to completely ignore it for that reaction. So basically, shear wall is only useful for the long direction only. Does that make sense? Yeah.
in the California building code that means you have to have two shear walls, one in one direction?
Yeah, two directions at least, right? So yeah, if you have seismic requirement, which I guess you do in California, yeah. Anyway, so that's kind of the assumption. So this one, it's very diagrammatical, and it's only trying to look at the lateral force this way. So that's why we're only showing the wall in this direction. But just so you know that this doesn't really work with a lateral force. If it's coming from this way, right, it doesn't do anything, right? But this is just for for explaining this direction. So, but know that, yeah. But that's important. It's kind of also, shear wall is like, it's kind of like a beam that's flipped vertical. So again, I never have a good thing, and I don't want to fold my books either. But you can imagine how, like, a beam, right? Like, do you have like a ruler or anything? Right? But anyway, beams, it's also kind of useless this way, right? But always useful this way. Like, the deeper the beam is, it's good at resisting the load. So the same thing if you were to flip that beam vertically, right? It's useful resisting the load this way, but it's useless this way. So that's the analogy between the shear wall and the beam. So that's rigid diaphragm. So that's kind of important to know. So the rigid diaphragm, the way the load gets distributed among the different shear wall is purely through the linear lengths of the shear wall. We're gonna be looking mostly at flexible diaphragm, which basically, so the diaphragm is again this horizontal slab element, right? So we're gonna assume that it's gonna bend almost like a beam, like that. So because we're assuming they're flexible, so it can take deflections, and that's how partially that's how it transmits the load to the shear wall. So in this case, though, that looks kind of different. Yeah. So what's different here is that you can see how now it has, if you look at the way the lateral force resistance in the shear wall is distributed, it has nothing to do with actually the linear lengths of the wall. Now it has to do with, you kind of have to look at it almost as a beam. So in a way, so it all has to do with the way it's spaced. So it's like it's three equally spaced bay, right? So that means basically that part will be taken care of by the wall on the left, and this half gets taken care of by this wall. But also this part, which is the midway between this wall and the next wall, so that red part all goes to that wall, right? And in the same way, the distribution keeps going. That part gets taken care of by this wall, and then this right quarter, that gets taken care of by this guy. So if you kind of look at the distribution here, now it's kind of like so it's all depends on, like, it's halfway between here and here, right? Halfway between here and here, halfway between here and here, and so that's the distribution. So now if you look at it, it's kind of like 2, 4, 4, 2. If you look at how much bay gets taken care of by each of the shear wall, that's why the resistance here is 40. So if you divide it 120 into 2, 4, 4, 2 chunk, it becomes 20, 40, 40, 20. So That makes sense, right? So this is pretty much the only time I talk about the rigid diaphragm. But know that rigid diaphragm, it's all about linear length of the shear wall. For the flexible diaphragm, it has nothing to do with the linear length of the shear wall, but it's the spacing between the shear wall. In a way, in that sense, it's kind of like a beam. So, which I think we're gonna, I mean, maybe not today, but the problems that I will give you on Wednesday will have that kind of a calculation. So we're gonna ask you to, like, I'm gonna have a wall layout, and you're gonna kind of calculate what the tributary areas are, and then, right, how much force gets resisted by the shear wall, right? But anyway, so let's kind of, so if you get lost, again, I will be following the explanation that I put on here. So if you get lost, you can basically kind of read through this this file. But let's imagine a very diagrammatic building like this, right? And I don't like the isocar. But anyway, so there's a building like that. There probably isn't if you look around, but this is this diagrammatic building for explanation. We have a shear wall and a beam. So beam, shear wall, a wall. I'm saying, you know, let's imagine that's like a curtain wall, and that's a floor slab, and it's a flexible diaphragm. And so all these sort of spacing, and so what you should note is that these shear walls are not extending beyond the entire length of the building. So that's only covering half of the building length. And again, if that's a curtain wall, right, so that's not resisting any lateral force. So if you actually consider this as an actual building, then it's not good for resisting a lateral load this way. So if there's any lateral load in this direction, this thing is just going to flip. And that's the end of the day. But again, this is just for explaining lateral force in this direction. So that's why it's a layout like this. So this is kind of a breakdown of. So this is kind of an exploded axon of what this building is, and it's kind of showing. We're kind of imagining a wind load that's gonna hit this front wall uniformly all the way across, right? Which again is also a pretty artificial scenario, because if you think of the actual wind, right, the distribution of the wind force would be almost like a topography map, because like some local points here would have like the highest wind or something like that. But you know, you don't really want to think about that right now. So we have this really artificial scenario of wind completely uniformly hitting across the surface. And so I numbered my comments. So yeah, so let's say, so I'll basically kind of like zooming into each element and explaining what there are. But anyway, so first assumption is that wind is blowing this way. And actually that's the only force we're looking at right now, right? So we're not even looking at the gravity. We're not considering any other lateral load. We are just looking at this wind. So this wind gets accepted by this curtain wall, right? And let's just imagine if you have this curtain wall. Let's well, curtain wall, that's a you know, maybe not a great term, but let's imagine that this wall is attached to a building at the top, but it's also attached to the bottom, right? So then the assumption is half of this wind load would go down to the ground directly. So that's where I said here, I guess, yeah. I guess, did I say anything about the... Anyway, so also another assumption is that this wind that's hitting the wall, let's just assume that it's a 25-pound force per square feet. So for each square feet, if you take 1 feet and 1 feet square, there's like 25-pound force that's pushing onto that wall. So again, yeah, I mean, don't worry too much about the calc, but we need something, right? So 9 feet, 9 feet, so 18 feet tall wall, 40 feet wide. So half of that will go to the ground. So therefore, that's 25 pound force per square feet, and the area of that portion of the wall is 9 times 40. So whatever the calc is, that's the total amount of force that's gonna go into the ground, right? The other half, which is the same exact amount, would have to go to the diaphragm, because if you look at the way this is attached to it, you know, this is going to the bottom and that's going to the top. So that's the diaphragm. But anyway, so the other half of the wind load goes to the flexible diaphragm. So this is like force pound per square feet, right? But it's kind of like you take this, whoops, but also it's kind of like if you take half of it, and you don't have to replicate this obviously, but it's kind of like if you grab this uniformly distributed force per square feet, it's kind of like you squish that 9 feet thick thing into a line. So therefore the wind load now, it used to be 25 pound square feet, but now you are counting all of this 9 feet thickness, so it becomes actually, so the total wind load on this surface, half of this surface, is 9,000 pound. But now you are going to kind of translate it to a pound per linear feet. So you see what's happening here. It's like, so this was 25 pound per square feet times 9 feet, which is the height, 40 feet, which is the width, right? But now it's you kind of divide that 9,000 divided by 40, and it becomes a force per linear feet. It's just a calculation thing, but you're just assuming that all of that force acting as one linear thing, right? So far it makes sense, yeah? Okay, so that now you have this uniformly distributed load on this edge of this flexible diaphragm, which looks familiar, right? Because if you take that and if you take that diaphragm and isolate it and go to the top view or something, and then if you rotate that, that's basically a beam, right? So you have a uniformly distributed load, it does this, right? So basically this whole entire flexible diaphragm acts like a beam, so it deflects like this. And if you remember how the beam behaves, right, if you do this, right, it gets compressed at the top and it gets stretched at the bottom, right? So you get the compression here and tension there. So that's basically how you come on. So that's basically how this flexible diaphragm acts, right? So then diaphragm is actually fully connected to these beams, which is called again, if you go back to this thing, so even when the shear wall is not covering, we would have this beam so that you can transmit it to the shear wall. But these beams are typically called, I mean, either way, I mean, both names are typical. So sometimes it's called collectors, or it's called lateral force collectors, or it's called drag struts. But this diaphragm or slab is fully connected to these two beams, which is the collector or a drag strut. at its entire length. So if you so it's like it's at every point on this edge you have this collector that's connected to the slab. So if you imagine that, then what happens is so this thing will try to move, right? But it's fully attached to this beam. So then for the entire length of this beam, it would experience this force, which is trying to push this way right now. So this diaphragm, which behaves like a beam, tries to deflect like this, right? But it's constrained at the edge, so it's gonna try to push this collector / drag struts this way, right? For the entire length of the thing, right? So that's where this explanation gets slightly tricky, but anyway, the diaphragm flexes with compression on the curtain wall side and tension on the opposite side. That's something I've already explained. But if you go to number 6, where's number 6? Okay, number 6, let's talk about that later. But if you go to number 7, the reactions on the east and west side of the diaphragm eventually are carried by the rigid shear walls, but there are, these forces are transferred by means of shear forces between the bottom and the diaphragm and the top of the drag strut. Okay, so that's the part that's kind of the whole meat of this explanation. But if you remember what the shear is, so this is why these walls are called shear walls. So if you remember what shear is basically what the force tendencies to try to. So if there's even there's a beam, even for a beam or for whatever, right? Like if there's a force this way and that way, there's a tendency to try to slide these two elements across each other. So that's what the shear is, right? And that's kind of exactly what's happening between these three things, right? So if you observe these three elements, right, this one is trying to flex, right? So I mean, it's actually flexing, and at the edge it's wanting to move, so it's trying to move this way, right? The wall is trying to resist that. This is trying to move, right? So this is trying to move this way, right? So this actually gets pushed that way, but it doesn't want to move, so it has to resist that force by trying to move the other way. The only way it can do it is, so this beam or the collector is being basically pushed on its upper side. So here the diaphragm is trying to move it this way, so there's a tendency to go this way. The shear wall supposedly tried to resist that lateral force. So if there's no shear wall, I mean, first it's gonna fall down, but if we ignore the gravity, if there's no shear wall underneath, and if the diaphragm is trying to push it this way, this guy is just gonna move this way, right, with the diaphragm. But it's not moving because it's being pushed back the other way. It's not being pushed back other way on the upper side, because on the upper side the only thing that's happening is the diaphragm that's trying to push this collector that way. So the only way this can resist is through the connection to the shear wall, right? So the shear wall now is gonna try to push this other way. So you see the two things happening. So there's one thing that's trying to push this long thing on this direction. On the downside, the shear wall is trying to push the other direction. So now you have this experience is shear, right? Because there are two opposite direction of forces trying to pass each other. So that's what's happening in here. And this is what's necessary to transfer the lateral force from here to there. So again, that was my reiteration of this statement. So basically, the reactions on the east and west side of the diaphragm eventually are carried by the rigid shear walls, but these forces are transferred by means of a shear forces between the bottom of the diaphragm and the top of the drug strut. So that's the shear here. And there's also so again, so that shear is also transferred from the bottom of the drug strut to the top of the shear wall. So if you look at the connection between the shear wall and this collector, it's also that, you know, this wants to move this way and this is trying to move the other way. So that's kind of the shear that's going on too. So that's the force that drug strut is experiencing from the shear wall, and this is the force that's the shear wall is experiencing from this side. Does that make sense? So this kind of like the chain reaction. The wall hits the floor, floor does this, floor wants to push this, you know, this thing happens between this and the shear wall, the same thing is happening, right? And so eventually, right, so this shear wall experiences shear, as its name, and it also experiences bending about its strong axis like this, right? So if the wall is fixed at the bottom, and if something is trying to push this wall at the top edge, it wants to bend like that. It's sort of like the cantilever beam or something like that. Anyway, so when that happens, right? So that's when I think that, like, eventually I want to have this like physical model to demonstrate it. But that's why I was trying to do that the other day. Like, if you hold this thing, right? So if I tell you to hold each end of this, like hold here, and you hold one end, right? So if I do this, right, you have to pull and you have to push up. If I do this, you have to pull and you have to push up, right? So that's basically what that diagram is, right? So that force right there is trying to rotate this guy. If nothing is happening at the bottom, it's just gonna topple over like that, right? So in order to prevent that from happening on this end, the foundation needs to be pulling the bottom of the wall, and the other side needs to be pushing the other side of the wall. Again, right, that's kind of similar to the beam too, right? Because the top part is compression, the bottom is tension and stuff like that. But also, like, if you, and presumably these the magnitude of these two forces, compression and tension, must be equal, right? And if you remember rotation, and you remember the term couple, moment of a couple, right? So the couple means a couple of forces refer to a same exact magnitude, opposite direction force, separated by a distance. So that's called a couple of forces. And what this does is there's a moment. So these two forces causes a moment about the center point, right? Because if you introduce two opposite direction forces on two ends, what it's going to do is it's going to rotate about its center, right? So basically, it's trying to. So these couple of forces are going to try to rotate something about this point. So that's a moment, right? So you can actually calculate the moment by these couple of forces, which actually should be equal to there's another moment here that's happening, which is the force at the top, right, to here, right? So this force is trying to rotate this wall this way, right? So that's one moment that's caused by the lateral force that's coming from the drug struts. These couple of forces is trying to resist that, and basically what it's trying to do is trying to rotate the wall the other way. Trying to rotate it the other way. As a result, when those two balance each other, this wall doesn't rotate. So that's basically what it's trying to do. So basically the moment between these two forces and the moment by this one onto this wall needs to be equal, assuming that the building is not moving, which is what you want. So anyway, the shear wall experiences shear, and it also experiences bending about its strong axis, symbolized by tensile force at its south end base and the compressive force at its north end base. But what I just said was basically a reiteration of that. So that's kind of how a shear wall resists the lateral force and why it's called shear force and so on and so forth. Does that make sense? Yeah. Okay, so I mean, this isn't super important, but so if you look at this simple flexible diaphragm, it's pretty much literally just like the beam, and you can kind of conceptually draw this moment diagram and shear diagram if you remember these for uniformly distributed load for the beam, right? Let's see. All right, so we're gonna get to do some of these. So this is not a problem yet, but this is kind of so I pretty much explained everything right now, but so the rest of that, whatever is happening here is an attempt at quantifiably explaining whatever I just said, right? So it's kind of accompanied by these calcs. So all right, so if you look at this one, so again, we're zooming into this diaphragm. The class is till 11:45, right? So I think we can finish slightly early. Anyway, so we can actually calculate the shear per linear foot, which is kind of an important concept. So before getting into this, right, you see how the shear that's happening between the diaphragm and the collector, right, which is along this whole length, like this tendency, that has to be the same amount as the shear that's going on between the shear wall and this beam. But you can see how the attachment or the lengths of connection, the lengths that's touching, the lengths that these two elements are touching each other are different, right? Like, so if you look at, okay, I just uploaded the video. Anyway, if you look at the connection between the diaphragm and the collector, you have entire lengths of the beam attached to the diaphragm. So that's the lengths of attachment between these two. If you look at the attachment between the shear wall and the collector, this is much shorter, right? In fact, in this case, it's half the length. But the total amount of shear between these two and these two must be total. So in other words, if you try to calculate the amount of shear per the unit length, it must be more intense when it's shorter than when it's longer, right? So actually, the shear that's between here and here, even though the total amount is the same, if you look at every linear length of these connections, there's more going on between these two. So that's basically what the shear per linear foot is about. So this is kind of isolating this element. So I'm saying we can calculate the shear per linear foot that the diaphragm experiences. These are the shear arrows shown here. So the diaphragm, it's trying to move this way and being resisted. So the shear it experiences from the collector is this direction, right? And the total amount of shear is obviously 4,500 because the entire, the total amount of lateral force is 9,000 and it's being divided equally between the two ends. But anyway, So this shear per linear foot is known as a unit shear and is represented by V. V represents shear, and I'm just gonna call it V roof because it's the shear on the roof side, and I'm calling the other shear V beam or something, V wall actually. Yeah. So I'm calling it V roof because it's the shear that's on the roof side, and it is simply the magnitude of the shear force divided by the length of the diaphragm. So literally the calc, I mean, it looks kind of daunting, but it's actually super simple. It's all about the shear divided by length of a diaphragm. So it's 4,500 because it's that was total 9,000 divided equally 4,500. If you divide it by its linear length, which is 20 feet, it's going to be 225 pound per foot. So that's the linear shear on the roof side. You can also calculate the linear shear for the beam side, or actually the wall side, which is on this side, which if you go back to this original diagram, you could see how the diaphragm was 20 feet long and the wall is 10 feet long. So the length is actually half. So sorry for moving around too much. But so again, the total amount of shear is the same. So the drag strut is responsible for transferring all of the load to the shear wall. The top of the drag strut feels the same amount of shear as V roof, so the linear shear is also the same, which is coming from the bottom of the diaphragm. The bottom of the drag strut, it's a weird word, but it feels the shear from the wall side, and I'm gonna call it shear V wall. That's what gets transferred to the shear wall. Anyway, if the wall extends under the entire bottom, so if the wall, it depends on the length of the wall, but in this case the shear wall is half the length as the diaphragm. So that's how we are doing the calc here, which is the total amount of shear, which is 4,500 pounds, is the same, but the length is half. So the linear shear actually ends up being double. Does that make sense so far? So I guess you can read that, but that's basically what I'm talking about here. So those two things we're gonna do a little bit of diagram later, but before I get into that one last thing is about this moment, right? So lastly, this V wall, which is this linear shear, is transferred to the top of the shear wall. This includes equilibrating shear at the base. Yeah, so this is again just explaining what I talked about briefly just then. Is so the shear here, the total shear here is 4,500 pounds at the top of the wall, right? And that's gonna try to rotate this wall about this point because the wall is attached at the bottom, right? So this force at the top has a tendency to rotate this guy about that point going that way. So if we calculate the moment induced by that shear is the height of the wall is 15 feet, right? So that's basically the distance between that point, perpendicular distance between the force and that point is 15 feet. So the moment induced by that shear at the top of the wall is 4,500 pound force times 15 feet. So whatever that number is the moment. And again, the important thing to remember, the unit for moment is always like pound force feet or pound, pound inch or pound force. Pound foot. Always a unit of force times unit of length. So this, we need to equilibrate that moment in this wall in order for this wall not to rotate, right? So that's when this tension and compression comes into place. So the the total amount of moment that's caused by these two needs to be equal and opposite of that, right? So that's why so the force, the vertical or the axial force of this tension and compression, we can calculate that from trying to equilibrate that moment. So the moment, let's say that's the positive moment, it's 67500 moment. So we need to be able to cause a moment on the other side, the other direction, by these two forces. So the resisting moment should be that much. These two forces are 10 feet apart from each other. So this is kind of a simplified way of calculating the moment by a couple of forces. So you can calculate the moment of two forces by, let's say the magnitude is F and distance is D. It's either F times half D plus F times half D, or you can just say that it's F times D, right? Because it's either this tension times 5 feet, this plus compression times 5 feet, or because we know these two are equal, you could just say tension times 10 feet. Either way, it should be equal to this 67500 divided by 10. So for each of these compression and tension, so this tension should be 6750 pound force, and this compression should be 6750 pound force. So you can, that way you can actually, so you see how this lateral force gets transferred to this linear shear, right? Eventually comes down to the top of the wall. That total amount of shear with wall height, that helps us calculate the exact number of this tension and compression at the base. So that's eventually how it resists. What used to be this horizontal force, it eventually gets resisted by, I mean, it has to get transferred multiple times, but at the end it gets resisted by a couple of tension and compression at the bottom. So going back to the linear shear, this is where I kind of it's been, you know, it's gonna be a little bit bumpy, but you have to kind of get used to this. So it might take a multiple attempt at getting this, but we will ask you to. So basically, this is a diagram that represents the linear shear along the length of this beam, right? So meaning that the shear, so even though the total shear is always the same, if you look at every tiny fraction of this beam, right? If the floor is hidden this way, and if there's a wall, right? So you basically have a wall and the beam, and you're trying to push this, and this is resisting that, right? So within this beam, the amount of shear it experiences is actually, as a total, it's always whatever that total number was. I think it was 900 or 4500. But if you look at every segment of this beam, it experiences more shear at certain points and other compared to other points. So this is kind of basically showing the distribution of the intensity of the shear along the length of the beam. And these are, and I'll show you how to draw these diagrams, and we will actually get the problems later this semester, actually like next week or so. We'll have more complex layout of shear walls, and then we'll get a more complex diagram. But this is the most simple case. But basically, if you think of it, so you have this collector or the beam or the drag struts, and above there's a diaphragm, below there's a shear wall, right? But now we are really trying to look at this beam. So, and I have this explanation. So each of that point So each of these explanations actually corresponds to that point, which is also at that point in the beam. So if you kind of follow this through, so first of all, there's this diaphragm which is shown as this transparent box. Let's hide this guy because that's in the way. But anyway, first at the very corner, right, the strut starts out with 0 axial force. So yeah, at the very end, even though this diaphragm tries to push this thing, at the very end, right, it's barely, nothing is happening yet, right? So there's 0 shear, unit shear here. But because this guy tries to push this along this whole length of the beam, it kind of accumulates and becomes more intense. And you should be able to kind of visualize that, because if you imagine this, let's say, I don't know, maybe we should make this out of like, let's imagine like a Snicker bar that's attached to a plate or something, and you try to push this thing, right? And it's attached at the bottom to this wall, right? It's gonna get squished, right? And you can probably predict like that's where it gets squished the most, right? Definitely not here, because that's like barely, that's when it's starting to accumulate. So it's kind of the same thing, right? So it's like it's getting pushed. Actually, so when you push the Snicker bar, you can't push it like that. You have to push it along the whole length at the top, right? But it gets accumulated, and so see how, like, so it says next it picks up compressive load per feet, increasing in compression, and it keeps increasing until it hits the wall. So that's where the peak is. And once you hit the wall, that compressive accumulated compressive shear decreases, because on the upper side you still have the diaphragm pushing this way, but now you have the shear wall beneath trying to push the other way, right? So that's what changes here. So up to here you only have the diaphragm pushing from above, but at this point you start to have this shear wall beneath that's pushing you in the other direction. So now it starts to change and gradually be equilibrated by the wall, so it starts to decrease, and the total axial force must equilibrate at the end, so it becomes 0 again at the end. I'll show you how to draw this maybe today, but anyway, so that's you kind of get the picture, right? This linear shear accumulates and then decreases, but it's always compressive force. If you look at the other side, so remember how these two walls are located differently. So I have this diaphragm going in this direction, but on the left side I have the shear wall at the far end. On the right side I have the shear wall at the beginning. So in this case the story is a little bit different in terms of the behavior of the drag strut. What happens now is you have a wall and you have this beam, right? And then this beam is like being kind of pushed in this direction throughout. So it's now like this used to be, if the force is going this way and if you see the wall, intuitively speaking, like you can kind of feel the wall is being pushed by this beam, right? But if you put the wall this way, and if the beam is being moved along this way, it's more like this wall is being pulled by the beam, right? If you look at this one, like so if I isolate these two, the important thing is like there's a constant force acting at the top side of these two beams, but you can see how that will, this is almost like pulling this wall, this is almost like pushing that wall. So that's kind of how it exactly happens, is that this unit shear, like from the beginning you have this opposite shear from the shear wall. So I should actually show this way. Sorry. I should show this. I should actually show this kind of like that. So, okay, so what's happening here is that unit shear on the shear wall side was greater, right? If you remember, it was double, right? Because the length is half, right? So the unit shear on that side is double. So you have more force pushing against you than, so the more force in this direction than that direction. So in comparison to the previous one, here you only had a force that's going this way. So in this diagram, I'm assuming the force in this direction to be positive, force in the other direction to be negative, right? So at the beginning, on this side, we only had this positive force, so that's why you had this like upward climbing slope. But here you have a positive force this way, but you have this negative force acting against you at the double intensity. So that's why you end up being more negative up until where you stop hitting the wall. And from there, it's only positive, so that's why it's starting to climb up again, but it always starts from 0 and it ends at 0. Do you see that kind of difference, right? So then, as a result, the direction of the force is different. So in this case, this beam is it's constantly in tension, but it starts out as 0. It peaks at where it hits the wall, and it goes back to 0. And for this tension, it's same exact thing, but it's the opposite, right? So, but the important thing is this beam is constantly in tension, but it's being pulled. Yeah. So, diagrammatically speaking, does that make sense? Right. So I'll show you briefly how to draw this diagram, which is always where I kind of become slightly challenging, but so in this case, let's see. So you have these two cases, and so everything is kind of so in this case, absolute scale doesn't matter too much, but it's almost like everything is kind of relative. But you have this case on one side and this case on the other side, and always it's, so the length is like 10 feet, right? Here it's 10 feet too. And the height of this diagram is somewhat arbitrary. Alright, so let's, in this case, I'm assuming the compression to be above. So if you, and let's say this axis is 0, right? And you don't have to draw this, I'm just explaining, right? So I'm assuming if the value is positive, it's compression. If the value is negative, it's tension. I mean, it can be vice versa, but however arbitrary it is, you have to make that assumption to start the analysis, right? Because like compression and tension is the opposite, right? So really doesn't matter what's above or what's below, but I'm just saying that the above is compression, below is tension, right? And so the assumption here was that, again, this is somewhat arbitrary, so I might end up getting a slightly different diagram, but so if I can copy some of these graphics, so if you remember, we had this linear shear acting at the top and the bottom of the shear wall. In this case, actually, that's the opposite. So sorry. So it should be going this way. Should be going that way. So this beam is being pushed in this direction because the lateral force is going this way by the floor above, and it's being pushed back by that much force by this shear wall. So the idea is the total amount of shear between this and this is the same, but because the linear length was half, the intensity here per linear foot was double, right? So this is more intense than the top. And I think the number we had was 450 or something, right? Let's see. So V roof was, let's say, yeah, it was 450 for this guy and 225 for this guy, right? So but the idea was that, so let's say there's 4,500 pound force shear total, right? But here it was 225 pound force per foot on the top side. The bottom side, it was 450 because the length was half. This absolute number doesn't matter too much. It's more about the relative. But you can see how, so basically the slope of this diagram, how it accumulates the shear, corresponds to this, right? It's kind of like if you draw a time and distance, that's the velocity, right? Anyway, so it's 225, so, and that's 10 feet, right? So again, if I draw 225, it's going to be too large, but it's almost like, so right now at this point up to here, right, up to here, so between here and here, so in this zone, the only thing that this beam is experiencing is this compressive force from the floor above by 225 pound per foot. So it's actually, so for every feet, let's say 12 inches, for every feet you're gonna experience 225, which is super huge. So I'm gonna do slightly smaller, let's say 0.225, no, let's say 2.25. Or maybe, so that's kind of what this linear shear is, which is if you go 1 foot over and then you go above, let's just arbitrarily say that's 225 pound, right? So that's what this graph does. And but we should also remember what this does to what's at the bottom. It has the force on the opposite direction and double, right? So the effect of this linear shear on this graph would be opposite of that. Whoops, sorry. And the magnitude is double. So the length of this guy is 22.5, this is 11.25, but that's arbitrary, but I'm just trying to show this proportionally correct. But does that make sense? So this, whatever goes up is compressive force per linear feet, whatever goes down is tension per linear feet. So because on this portion of the graph I'm only experiencing this linear shear, so the graph accumulates at this pace for 10 feet, right? So this keeps going up, extend, so this graph should, whoops, what's going on? So this graph keeps going up that way, right? After you hit this line, right, what happens is now you not only have the effect of this force, which is this, but you also have the effect of the other force, which is the opposite direction and double. And that's why it actually turns into a downward slope at the same slope. You know what I mean? Like it's actually going up by 1, but it's going down by 2. Therefore, it goes down by 1. So that's how this graph turns into a downward slope by this much. And I must have had a different scaling, but the whole point being the actual height of this diagram doesn't really matter in this case, because we're not trying to calculate from this diagram, but this diagram is just visually communicating what's happening here. So you can actually use whatever scale to, as long as it's proportionally correct. So any of these diagram is right, but it has to be starting from 0, upward slope, peaks and comes down, right? So that's why this diagram does that. And similarly, because on this other end, because you have this resisting shear from the wall at the bottom at the beginning, right? So now instead of having, so you have this shear in the beginning, but you also have the wall resisting that shear. So for this, right off the bat, you have these two opposite forces working. So that's basically kind of what's going on from the beginning, is that, so you have 0 here, and basically you have this linear shear. So it starts here, it goes up and goes down. And so that's the first portion of this diagram. So it starts as this downward slope. Right, so that's why it starts out as a downward slope, and let me just kind of move it up. But once you go past that wall, you only have this top shear, so that turns into this positive, because it's only going up because it's only that compressive force, and it becomes this upward slope. And therefore the diagram ends up looking the opposite way. So it happened to be this half length, so it just becomes this really simple one, but you can see how the diagram is going to be different. For example, if the wall was like, the length of the wall was different, this diagram is going to look different. But that's basically how we translate that to this diagram, and we're going to be actually drawing some of these diagrams, but hopefully it makes conceptual sense. And that's basically it for today.